In today's lesson, we will learn about some advantages and some disadvantages of dimensional expressions. First, we take a look at a few advantages of the dimensional expressions. In this topic, the first advantage for dimensional expression is that we can find the components of any physical quantity in terms of mass, length, and time. Let us take a simple example for this. We take the example of work done or energy, and the formula for work or energy is given as force into displacement. Further, if we break down force, then we get what? What is force? Force is mass into acceleration. So let us go for the dimensional analysis. So force is equals to mass into acceleration, and displacement is denoted by the letter S. Now let us put the dimensional expressions of mass, acceleration, and displacement. These are the dimensions of mass, acceleration, and displacement. Mass is m1, acceleration is L1 t minus 2, and displacement is simply L1. Now, if we algebraically treat all these three square brackets, what do we finally get? What we get is this: the dimensional expression for work done, m1 L2 t minus 2. So, we have found out that work done depends on mass, it depends on length, and it also depends on time. Now, along with this one advantage, let us discuss one disadvantage also. That is, now we are going to find out the dimensions of both kinetic energy as well as potential energy in the same way like we have found the dimensions of work done. Okay, the first thing we should know the formulae of kinetic energy and potential energy. So let us start then. The formula for kinetic energy is half mv square, as we have learned in class 9th. Now, from the formula, we can see that it is made up of three terms. The first term is half, which is just a number and it is not a physical quantity, so it will have no dimensional expression. For mass, the dimensional expression is m1 L0 T0, and for speed, it is m0 L1 T minus 1, but because you see is square over uh, uh, the velocity, you also have to put a square over the dimensional expression for velocity, which goes like this. Square. Now, analyzing or mathematically treating these, what we finally get is the dimensional expression for kinetic energy. What it is? It's m1 L0 T0 multiplied by mass 0, and this is 2, so this becomes 0. L1, but it has to be squared, so we get it as L2, and again T. The power of T is minus 1, which is again has to be squared, so this becomes minus 2. Finally, what we get from this is m1 L2 T minus 2. So this is the dimensional expression for kinetic energy. You can see the dimensional expression for work done, m1 L2 T minus 2, m1 L2 T minus 2. So in fact, work and kinetic energy, they have the same dimensional expression. There are other physical quantities also which will have the same dimensional expression, such as potential energy. Now, the potential energy, the formula we already know for it. What is the formula? We learned in class 9. It is what? It is mgh. Now, m stands for mass, g stands for gravitational acceleration, which is same as acceleration, and h is height. I'm leaving this proof to you, but you have to find the dimensional expression of potential energy by yourself. However, the answer I am telling, what the answer or the dimensional expression for potential energy will be, it will again be the same: m1 l2 t minus 2. So you see that work done, kinetic energy, potential energy, they all have the same dimensional expression. So this is one disadvantage of dimensional expressions, that many physical quantities can have same dimensional expression. We learn one more advantage of dimensional expression, and that is to find new relations to derive uh, some new physical quantity. And for this, we take an example of a pendulum. We will calculate the time period of a simple pendulum. Now, what is a simple pendulum? It's nothing but a string which is tied to a bob and which is free to oscillate in vertical plane. Say very simple like this. You have a rigid support at the top. This is the string. This is the bob. The length of the string is L, and say the mass of this bob is M. Okay. Now what is the time period of this? Let us understand first. See, if I displace this from its position, that means if I take this pendulum over somewhere and then release that pendulum, then the pendulum will start oscillating like this. It will go here, then it will come back, then again it will go over here and come back, and slowly and gradually it will come to stop. But whether the pendulum is making big oscillations, or even when it is making small oscillations, that means if it is oscillating between these 2 points like this, or it is oscillating between these 2 points like this, one thing remains same for both these oscillations, that is the time period. Okay, so how do we define this time period? We start time equals to 0 at this point. The pendulum goes at the other end. It comes back at the same position. Now, the time that is spent during this one oscillation, going here and coming back, this time period, this time interval is known as the time period of simple pendulum. Okay. Now, we exactly do not know that on what factors the time period of a simple pendulum may depend on. So we make a wild guess in this. Now this is the wild guess. This is which I'm making. Say I have formulated that. I have guessed that the time may depend on length of the pendulum, the length of the string. It may depend on the acceleration due to gravity, because it is all moving under the influence of gravity, and it may depend on the mass of the pendulum also. It may happen that a heavier bob may pendulum, the heavier is the bob, it may affect the time period of oscillation, but still I am unaware whether the time will be directly proportional to length or inversely proportional to length. Okay, again I am not knowing that whether the time will be directly proportional to gravitational acceleration or it is inversely proportional to gravitational acceleration. That means time increases with g or decreases with g. I am not knowing this. So for this purpose, I am putting again some very wild guesses. Let it be A. Now if time is proportional to time is directly proportional to length, then a will be positive number. And if time is inversely proportional to L, that means if the relation is like this, 1 by L, then a will be a negative number. Now I do not know exactly what is going to happen. So this is again some wild number a, again this is b, and again I am not knowing that how does it depends upon mass. So let me say it is c. So the overall conclusion that I am making is that time may depend on length to the power a, gravitational acceleration to the power b, and mass of the pendulum to the power c. I'm not knowing what are the values of a, b, and c, and now I'm going to find out what are the uh, values of a, b, and c, which will make the thing clear. Now, length. What's length? The dimensions of length: m0, l1, t0, and the power is a. Then comes gravitational acceleration. What is it? It is m0, l1, t minus 2, and what is the power? The power is b. And mass, what is mass? It is simply m1, l0, t0, and the power is c. That is the right hand side of the expression. Now coming to the left hand side of expression, we have only one variable, that is t. And what a dimensional expression for t? Dimensional expression for t are m0, l0, t1. Okay. Now this is the field in which now I have to play with. Now the next step is to compare the dimensions of LHS and RHS. Okay, we first open this entire expression and let us see uh, what does it comes to. And this is how it actually happens. Just expanded this m0a, so this m is 0, l to the power 1, and then again to the power a, so this is la. T is 0 to the power a, that is again t to the power 0. Now for gravitation acceleration, m0 to the power b, again m0, l1 b, so l to the power b, t to the power minus 2 to the power b, that is t to the power minus 2b, and in the same way for mass. Now again we have to simplify all these things for m, l, and t. Now as you can see, I have done some algebraic operation. When the base are same, the powers can be compared. So I have added all the powers. M has power 0 plus 0 plus c. The power of L is a plus b plus 0. Okay. T has the power 0 minus 2b plus 0. So this is 0 minus 2b plus 0. And on this side, there is only time which plays a role. So this is m0, l0, t1. So now I can compare these dimensions. See, the power of m over here is 0 plus 0 plus c. Okay, that is equals to c. And what is the power of m over here? It is 0. So one thing is sure, c is actually what? It is 0. Coming to L, comparing the powers of L on LHS and RHS. Here the power of L is 0, and on RHS the power of L is A plus B. So A plus B equals to 0. Okay. Now coming to again LHS, the power of T is what? The power of T is 1, and on the RHS the power of T is you can see is what? Minus 2B. Minus 2B. Okay. So what is to be done now? I have to find the values of A, B, and C from these equations. The easiest value to find is the value of B. see 1 is equals to minus 2b, so can I write b is equals to what? B will be equal to minus 1 by 2, and you can see a plus b equals to 0. So if b is equal to minus half, a is equals to plus half, okay, and c, it is already equals to 0. Now what is the meaning that c equals to 0? We will discuss it later on, that what is the meaning of c equals to 0. Now again, because I know the values of a and b, I can substitute them in this equation, a then b, and see what do I get. What do I get is this. Just see, I have done nothing but some substitutions. L to the power a, L to the power half, g to the power b, g to the power minus half, and this is now a mathematical expression. Can to the power half, that means, what does that mean? In mathematics it means the square root of L, okay. G to the power minus half, what does that mean? G square root, but negative shows that this is not in multiplication, this is in division. So finally I come to this result, that time period of simple pendulum is L by G square root. That's it. And the meaning of c equals to 0 is now obvious, that the time period does not actually depend on the mass of the pendulum. Okay, this mass, whether it is heavy or whether it is light, it does not depend on mass. The time simply depends on two things, that is length of the pendulum, this length of the pendulum, and the acceleration due to gravity. Okay, now if I have the same pendulum and I measure the time period of that pendulum on earth and then on moon, where do you think the time period will be more? Just compare the values of g on earth and on